So much for joining today. I'll do that one more time. Hi, everyone. Thanks so much for joining today. I'm really excited to share with you some information about planetary defense, specifically with respect to asteroids and comets that are in our solar system. So let me go ahead and share my screen and we'll get started. So I'm Eileen Ryan. I'm the director of the Magdalena Ridge Observatory 2.4-meter telescope. I have been director for the last 20 years. So we're a fully operational facility within NASA's program. And so I'm going to tell you a little bit about what we do with respect to planetary defense and also sort of focus on what we can do in terms of future progress, future technology. Uh-oh, my slides are not advancing for some reason. Let me see. Let me see if I can click on them. Yeah, there they go. So just to get some background information, here's a plan view of the solar system. So you see the circular blue lines are defining the orbits of different planets. We have the sun in the center and the inner planets, and then the last circle is Jupiter's orbit. You can see a green haze between Mars and Jupiter. All those green little dots are in asteroids in the main asteroid belt. That formed because a planet failed to coalesce between Mars and Jupiter in the early solar system formation. So we have tiny individual objects all the way up to tens and of kilometer size objects and larger in that zone. And they orbit the sun just like the planets do. So it's a very orderly system, except some of you might have noticed the red dots. So the gravitational perturbations from Jupiter and the sun cause those green dots to be diverted into Earth crossing orbits or interplanet crossing orbits, and they become red dots. And that's what we call near Earth objects. Those are objects those objects have orbits that could cross the Earth's orbit. And that's a troublesome problem because this is an area that it could have been a planet in the main asteroid belt, but it wasn't. So we don't absolutely positively have a survey of every object that's out there. We have to find what's out there and then also track their orbits and understand what they're going to do in the future. And so thank goodness for orbital mechanics and physics because we have a good handle on that, but we do have to search for them. So that's where our telescope comes in. At the Magdalena Ridge Observatory is located in central New Mexico on top of 10,600-foot peak. There's a picture of our observatory on the image on the left with a time lapse showing the beautiful rotation of the Earth against the background stars with Polaris in the center, keeping stationary. And on the right, the image is of our 2.4-meter telescope. So what advantage we have within NASA is that we're one of the largest telescopes working within NASA's Planetary Defense Office. And as I said, we've been working for over 20 years with NASA on this project. And we have several different capabilities to offer NASA that's unusual. We also work for national security so that we look at artificial targets and satellites near Earth and also around the moon. And so we have a capability to go at what we would say slew or move very, very fast in the night sky. So we have 10 degrees per second slew rate and 3 degrees per second squared acceleration rates, which are 10 times faster than a normal astronomical telescope. since we're a dual use telescope. So that's very advantageous for productivity and also tracking very close approaching asteroids that are moving very fast. Another aspect that we have is because we were designed to do missile tracking as well as regular astronomy. We can look 2 degrees below horizontal. So a lot of times we can see objects that are very low in the sky, the night sky, and that's an advantage, giving NASA some opportunity to almost have us act like a southern hemisphere telescope. So we can see very eccentric orbit objects, comets that are low in the northern hemisphere sky, but we don't have as many assets in the southern hemisphere to follow up on them. I gotta keep clicking my slide to advance. There we go. So again, the program itself is important in that the first line of defense that we have, whoops, did I go back? Is to make sure that we can find everything that's out there. And in a sense, we need to have a synergy between telescopes like ours. The 2.4 meter is a follow-up telescope. So we have search telescopes, search and discovery, and then follow-up telescopes that work in tandem so that we can detect these newly discovered objects that are in Earth-crossing orbits that have been kicked out of the main asteroid belt and sent our way from gravitational perturbations. And so the discovery telescopes find them, but they have a very short arc of discovery, so a very short amount of time. So if you want to try to draw a circle around something and you have just a few points, you're not going to get a very, very accurate circle, right? You want to have that maybe 10 points instead of 4 points. And so you need another telescope to come in after the Discovery telescope finds a new object and then extend the arc of that orbit so you can very accurately detect and understand what the object that you're looking at is. Is it a threat to Earth? Is it not a threat to Earth? All those things have to be assessed after first discovery. You can also do a lot of science in this project. You can take data with other instruments to understand composition. That's a spectrometer. And then you can infer internal structure from rotation rates of asteroids and also sizes from reflectivity and just basic color data. But we do need to have as our first line of defense is not that we want to think of the asteroids and comets as enemies, but it is like know the enemy is our catchphrase. We want to find out what's out there and is it threatening to us and what can we do about it. So we have to find them, get great orbits for them, but then we have to also do continual surveying to find new objects because we don't really know everything that's out there. And then also make sure we understand the orbital changes through time. So here's a daytime picture of our telescope facility, and then just on the image on the right is kind of what I just described verbally for you a minute ago, that we have the Earth there as a green circle and a dot, and then we get a first orbit that you see, that very largest circle on that image. It's the initial error ellipse. And you don't really know how accurate that is. But then as the follow-up telescopes come in and take data for the first night, you get that smaller circle zeroing down in the center. And in that particular case, you might think, oh my goodness, this might be a threatening object. It looks like it's coming very close to the Earth. And so that is something that you really want to pay attention to. But then you go in and maybe extend it 2 or 3 days in the arc of the orbit, the uncertainty reduces such that, oh, well, it's going to miss us. It's that tiny little circle or whatever. So that is the basic principle behind it, is that you need to keep, you have to find them and then assess their orbit. Oops. So, how dangerous are these objects when we find them, and how much have we found? The Space Guard program that NASA started was in the early 1990s. So it's been a while that we've been looking at these objects and trying to find out more about them. If you can look at this particular schematic, it shows you the hazard by size and how much we know about that. So the very largest objects on the right, that is pretty much the objects that are 10 kilometers or larger. We know about 100% of them. We haven't not found any of the big guys because that's fairly easy to do with ground-based telescopes, and we have some space-based telescopes as well. So we know most of those, 100%. The 1 kilometer objects, we have pretty much 90% of those known. And these two statistics are really great news for the Earth because if a 100 kilometer object hit, that would be global devastation. If that type of object was on an Earth crossing orbit and we were at the same place at the same time, that would cause mass extinction of terrestrial life. So we don't want that to happen. We don't want that to sneak up on us unsuspected. 10 kilometer objects that we know 90% of, we believe that that particular size regime can still cause global devastation and the possible collapse of all civilization. So those are the two things that we had focused on since the early 1990s, is making sure we could find the big ones. And but as we went further on and got better telescopes and larger telescopes like our 2.4 meter, we realized that, well, it's kind of bad to have global devastation, that's for sure. But how about things that are in the 100-meter size range? Could that still cause a problem? And the answer is yes. It can actually cause a crater on the surface that's 1 or 2 kilometers in diameter. And that would actually be a city killer or a state killer or even a continent killer in some cases, depending on angle of entry and speed. So that is something we have been focused on more lately, since more the 2000s, the 2010s, and we only know 42% of the objects in that population. So don't have nightmares, but yeah, it's still a work in progress. And then 25 meters is the borderline for where if an object comes in, normally our very thick atmosphere would cause it, the stresses of going through our atmosphere would put a tensile force on the object and rip it apart. So we call that an airburst. But it still could cause widespread injuries if it airbursts over populated areas. And we have had a couple of instances where that has occurred, and I'll talk about that in the next couple of slides. And then something as small as 4 meters, we really don't know much of the objects in the 25 meters or the 4 meters. There's so many millions of those out there, but there's still a concern. And the 4 meters generally are what we call shooting stars. They look beautiful in the night sky. They're a bright flash. There's no ground effects, but they could leave meteorites. So that's kind of like a treasure hunter's dream. If you can have an airburst, that's something you have to be careful about. But something that's very small and that breaks up, and all that it leaves is a beautiful streak of light. Now that's the one we don't have to worry about at all. And so here is that same schematic, but in more of a graph form, if you guys think about it that way. So this is just a summary of what I was saying. The horizontal axis is asteroid size, the diameter of the asteroid, and the vertical axis is the estimated number of near-Earth asteroids in that category. And the percentage of near-Earth asteroids discovered is the blue line, and where the number is the red line. So we have most of the objects under control. Again, in the continent and the global region, there's still quite a bit of uncertainty, 20%, 10%, up to 40% in some of the size regimes. And then on this graph, it also denotes what would be the impact if the object hit us, the city killer, the regional killer, the continent killer, and the global killer. That's the case where there's nowhere to run. And so we have two incidents of the airbursts that have struck us in the past that were potential city killers. We have the Tunguska impact that occurred in the early 1900s, and that was an airburst that flattened many square kilometers of forest, but it was in an unpopulated area, and the only loss of life were reindeers. Sad but true. And the more recently in 2013, the Chelyabinsk airburst. Now that caused a little bit more trouble, so I'll talk about that in a couple more slides. But then you notice that the larger object, the one that it's around 10 kilometers in size. Now that's a problem because we um, we do have this as a data point, and it's very definitive that there was a asteroid that hit off the coast of the Yucatan Peninsula in the Cretaceous period, and we have evidence with an iridium layer that is observable all over the surface of the Earth, and that caused 85% of all life on Earth to become extinct, including the dinosaurs. So we don't want to be in that category. We don't want to be like the dinosaurs and have a dinosaur killing crater hit. But here's a 3D image in this particular slide of that crater, the Chicxulub crater off the coast of the Yucatan. It was half on water, half on land when it impacted. It was 65 million years ago. It caused a crater 180 kilometers in diameter. That's for a 10-kilometer crater. So generally the crater created from an asteroid traveling very, very fast, something like 30 kilometers per second, can create that large, like 10, 20, 100 times larger than the actual objects. So we also have plotted here in this view of the Earth, the map view of the Earth. We have where we have well-studied craters that have been on that size range, and so it's not as bad as the entire civilization killing, but they're pretty large craters. And you can see in the more populated areas or where craters have been studied. And of course, you see ocean being blank. It's harder to discover craters there. And Earth has a lot of geologic activity, so there's a lot of resurfacing. A lot of craters have been erased. But just think about it when you look at the moon. It's all the craters that are on the moon, all the impacts that the moon has suffered is exactly how much the Earth has suffered as well. So we are in no special environment, but there's constantly over the 4.5 billion years that the solar system has been in existence post, formation. We've had all the same craters or all the same objects, asteroids hit us as have hit the moon. So the airburst events are also mapped here. They occur much more frequently. There are objects in the 20-meter or around that size that come through and the atmosphere rips them apart in the air. And you can see those. We have different monitoring stations that map these airbursts or fireballs, some people call them. The one that is, I mentioned in the previous slide, the Chelyabinsk meteorite exploded over the city of Chelyabinsk in Russia on February 15th, 2013. And you can see the one boulder that fell in a frozen lake, that's the asteroid that fell. Just a piece of it, though, a small piece. It was broken up. And you can see that people had video of it because they were going to work. It happened around 9 o'clock in the morning, and they were driving to work. And a lot of people have video cameras on their cars, and you can see the fireball coming in and hitting that city. And just as a little bit of a history lesson, it was actually quite good that we have good scientific cooperation, and there are no difficulties with communication, because Chelyabinsk was a former munitions factory for nuclear weapons during the war and also the Cold War. And so this particular event could have easily been mistaken for a nuclear missile launch and delivery. And thank goodness that people were right away asking scientists what's going on, and there was great amount of data being shared, and people could relax that it was not a threatening military action. It was a natural phenomenon. So, but this particular airburst caused such a pressure wave in the atmosphere that it sent 1,500 people to the hospital, ripped off roofs, and shattered glass windows in the entire city of Chelyabinsk. So it was a lot of damage, even though it exploded in the upper atmosphere. And we also have objects that, here's some pictures that we've taken with our telescope that we can see. I have green circles around the asteroids. There's 2015 VY105. That it actually passed through the geosynchronous satellite belt. So it didn't hit the Earth, but it hit the region where satellites are. And so you can see one streak on the bottom is a geostationary satellite called Teeters 3. And then there's some star trails because the telescope is tracking on the asteroid, and you can see how close it came to some of the satellites that are out there. Now, that would be a problem, especially for national security, if it came close to one of our spy satellites. But also, hey, if it came close to the Dish Network or DirecTV, I'd be mad too. So it would be a definite thing to want to know if one of those if an asteroid was going to hit a satellite. And we often get debris that come through very, very close to the Earth. And space debris is the object that I have shown on the left. It actually hit the Earth off the coast of Sri Lanka in 2015, the same year. And it is something that's interesting because you can now, if you can find it before it hits, which is what that image is showing you, the telescope found it, and then we knew where it was going to hit. We could predict where it was going to hit. Then it's something you can do something about, or at least warn people on the Earth. And here's another example. Of an asteroid that was discovered in 2024. It was 2024 RW1, and it's shown there on the left circle. We discovered it less than 12 hours before it was going to hit. So we warned everyone that particular night. We were one of the first follow-up telescopes to find it, to follow up on it after it was discovered, so we could get an accurate orbit, and the Jet Propulsion Laboratory could do the orbital dynamics to tell where and when it was going to hit. And I think it was down to the second, and like just 10 or so kilometers. It actually very accurately predicted when and where. And people were notified in the Philippines, and people got video of it coming in. It was safe off the east coast of the Philippines. It landed in the water. But that's a cool video picture of an object that did hit the Earth, but it was small enough and landed someplace safe, like the ocean. Unpopulated, at least. So we also were very much involved in the Apophis follow-up effort to make sure to reduce the risk that this asteroid would hit the Earth in 2036. There's still a lot of controversy about, people were very concerned that Apophis is still it's going to pass through, a close approach in 2029. And the United Nations has named that the International Year of the Asteroid. And it's going to make this very close pass. But we expect, we'd have to watch it, make sure we get additional information on the orbit after it makes the close pass. And then we can assess whether or not it's going to be a threat after it is interacting with Earth's gravity. But as far as we know from the data we have right now before the close approach and our estimation of after close approach, it won't hit the Earth. Okay. So, but another asteroid just recently that has been quite a concern is 2024 YR4. So this is not the airburst size that I've been discussing. This is something that's about 67 meters in diameter, and it was discovered just about December 2024. So the intense observations were done in January of 2025 and after. And it has the distinction of having had the highest impact probability since the NASA Space Guard survey has begun. It got as high as a 3% chance of hitting the Earth in the year 2032. It was extremely dangerous for a while, but we had all of the telescopes in the after the discovery, so all the follow-up telescopes have to come in, and us, along with some 5-meter class telescopes and also space telescopes, were working for months, initially about 3 months to track it. And as it got very, very faint down, we were able to track it till it got a visual magnitude of 25.5. That's pretty much the limit of our telescope at 2.4 meters. So that's the light bucket that we're collecting, and that's about as faint as we can see. But we got very accurate data together with the other telescopes, and we're able to reduce the risk to zero as far as we know today. So we still have to keep a watch on it. It does have some other impact hazards associated with it, but I have a picture, an artist's rendition of what it might look like with a Boeing 747 superimposed on it. So that's how big a 67-meter size asteroid is that size, like 747 size. And so, again, while we were really worried about Earth, it was initially 3%. It rose to a 4% impact probability, and then we reduced it to zero. But then when we looked at the data again, there was the James Webb Space Telescope. It helped in the reduction. But we were very concerned for a while because the asteroid was also as a target to hit the moon. So we had to take additional data as best as we could because we really wanted to make sure that if it was going to hit the moon in 2032, and we are planning to send humans back to the moon, and we have the Artemis mission ongoing, that would be something very important. So if we're going to expand to have lunar bases, now we have to worry about our neighbor, the moon, as well as the Earth for these near Earth crossing objects. And we don't have just the main asteroid belt and also the Kuiper belt where comets generally come from, which is outside the orbits of Neptune. We have objects now that are being discovered, 3 or 4, that came from outside of our solar system. The first one that we had worked on was Oumuamua. That was discovered in 2017. Oumuamua means scout in Hawaiian. So this is again an artist's rendition of what that object would look like. And I'm sure you could imagine what the internet speculation was at the time. It kind of looks like it could be a spacecraft disguised as an asteroid to survey the inner planets of our solar system. And so one of the tasks NASA actually assigned us to do as a telescope in their network was we were tasked to make sure we followed it for 3 months straight to make sure we got where exactly the outgoing and the incoming trajectory was. And it looks like it came from Proxima Centauri, one of our closest stars. But it's a kind of a cool result because that means other stars also have asteroid belts and planets. And maybe there's people or some kind of life around those types of systems. So, we have an interesting aspect that we're not alone in the universe, that there's a similar solar system formation around stars, and other stars in our galaxy, as well as probably other galaxies with all the galaxies that are out there. So it was a very interesting object to work with. And we have, again, found about 2 or 3 more of these objects that came from outside of our solar system. And we were able to report to NASA that the object followed a natural orbit trajectory. It wasn't speeding up or slowing down to take pictures of the Earth. So that reduced some of the conspiracy theories that were abounding at that time after discovery. So, okay, so here's all the asteroids that threaten the Earth. Now, what are we going to do about them? How can we protect the Earth and give, Earth some warning time, or at least to evacuate or potentially deflect these objects from actually hitting the Earth? So what can we do? So that is where we did a scientific study where the mitigation techniques for potentially hazardous asteroids were studied, and we found that through a panel of experts looking at what was the easiest thing to do. Well, we could use a gravity tractor, we could blow it out of the sky, we could use a nuclear bomb, or we could use something called a kinetic impactor. And that was what was suggested that we do in terms of NASA's first test of deflection of an asteroid was to focus on kinetic deflection. So that was the DART project. That was the first, it's the double asteroid redirect test. And it was NASA's first planetary defense mission. It was launched specifically to impact the spacecraft itself, which is vending machine sized, was going to impact the moon of a binary asteroid. So in this image, you can see, I don't know if you can see my cursor, but here's this little moon Dimorphos, and then here's this larger parent body, Didymos. And so this binary asteroid pair was a perfect example of a near-Earth asteroid pair that we could send this vending machine-sized spacecraft to, hit the moon, and see if we could change the moon's orbit safely around its primary body. So sounded perfect. And our telescope, the MRO 2.4 meter, was one of 4 funded ground-based support telescopes that had the task for getting the information about how the orbit changed. So this is a sort of a layout of what comes next. The spacecraft was going to impact Dimorphos, and it did so on September 2022, September 19th, 2022, and when it was in a close approach to the Earth. And then the next would be to at least change the orbit time or the orbit characteristics of that small moon Dimorphos around Didymos by at least like 73 seconds or larger. We would figure that that would be an impact enough, you know. And so the poor little spacecraft was going to take pictures all the way up to the end and where it crashed in to the surface, and it was impacting at about 6 kilometers per second. So it was going to create a crater, and then we were going to see if that changed the moon. And in a second, I'll show you the size scales that we're dealing with here. And then, so after that, we would have to use ground-based telescopes to understand how much that orbit changed by taking specific data called a light curve to see before. We took a lot of data what the orbit was prior to the impact, and then we would compare it to what the orbit was after the impact to see if there was a change, if any. So this was kind of cool because we had prior to this mission in September 2022, we had several Hollywood movies that depicted an asteroid headed towards Earth, but its civilization was destroyed. There was nothing anyone could do. So we had Armageddon, Deep Impact, and then Don't Look Up that looked centered on this topic. But this time it wasn't a movie. This time it was really something we had to worry about. And what we were gonna do about it, we were hoping would be successful. So in terms of the size scale, this is a schematic where the kinetic impactor will deliver kinetic energy, and that is 1/2 the mass times the velocity squared of the impactor, and that would hit Dimorphos. And you can see the difference between the DART spacecraft is about 19 meters in diameter if you include the solar panels. Here's the Statue of Liberty. Here's Dimorphos, the poor little moon, 163 meters in mean size. And then Didymos, which was the parent body of this binary pair, is One World Trade Center size and larger. So that's the type of impact we're doing. So the mass of the spacecraft was 579 kilograms. It was traveling at 6.14 kilometers per second. So it delivered about 10 billion joules of kinetic energy to this system. And here's that time lapse of the spacecraft was 90,000 kilometers away from Didymos. And it is kind of, you can see a little tiny pixel in there. It was run by the Johns Hopkins Applied Physics Laboratory, and they did a fantastic job of autonomous navigation based on their past spacecraft missions. So they had a lot of experience with this. And their smart nav system zeroed in on the pixel, and then they got 25,000 kilometers away. Now you can see it's more 8 pixels across in their camera, and Dimorphos is starting to show off it's only 2 pixels. And then you get 920 kilometers away, and you can see the system Dimorphos and Didymos here. And then this is the last image of as the object, the poor spacecraft hit the surface of Dimorphos, and this was the penultimate image before it blue screened, and we got this. But we don't have a picture of the crater. The European Space Agency is launching a mission to go back to this asteroid pair and take orbital images of the crater. So we'll have to wait for that in the future. So here's another good schematic about how we were going to do this. Here's the Dimorphos, the little moon. Here's a schematic of the spacecraft coming in and to hit it. And it all went really well. It was a bullseye shot. Here's our main parent body, Didymos, and then we had to collect the data to determine the orbit. We understood that we could have the spacecraft hit the asteroid and have really no debris or ejecta being produced in the event. We could have a middle result, which would have moderate ejecta, or we could have heavy ejecta and a large momentum increase. So we'd have an extra thrust. So not only would the kinetic energy be delivered, but we'd have some material being blown off the object, which would give it a thrust that could potentially change its orbit even more. So you can see here, it's a spoiler alert. This was the original orbit of the asteroid Dimorphos around the parent body Didymos after we hit it with our DART spacecraft. This is the new orbit. So it was hit. You have to think about Kepler's laws here. So we have the object slowed down, and then so it assumes an orbit that is closer to Didymos, and then we have it. The end result was that we were hoping for something that would be about a minute. It would take a minute difference or so, and how long it would take then to go around Didymos, and that would be what we found was it actually was 32 minutes of a change. Here's some pictures that we took shortly after that impact, because again, we're very low on the horizon. It was a southern hemisphere observable object, but we were able to see it just 10 hours after impact at nighttime. You can see the debris and the blast is still visible. So that's Dimorphos Didymos system there in the middle. And then 34 hours after impact, you can see a tail of debris forming, and then 58 hours after impact. And that tail persisted for 6 or more months, and it extended many, many kilometers. So it was an amazing amount of debris. And so we were able to use, again, a more global approach. We had telescopes on every continent around the world. And so ours was the only North American telescope that could get the images because of our strange capability. But we had some Hawaii results, and then the rest are Southern Hemisphere, and some Europe results as well. So how are we going to measure that change? How are we going to understand the new orbit of Dimorphos? Well, it is basically looking, so here's a schematic of the telescope on Earth. We'll look at the system, and it will follow the light variation as this object orbits around that object. And we can see peaks and dips when the light combines, or when the light is side by side, or when the light is occulted behind. And so you have a very good idea of what the orbit is, but you could tell how long it takes to go from one peak to one trough, and then you can estimate that. And so that's called a light curve, and that's what the telescopes, including us, were able to do. Here's an example of it's kind of it's more of a complex system when it's a binary pair. I've got a lot more analysis to do for our telescope. And so these light curves, these are two examples, one very soon after impact in October 11th and then October 21st. And again, the orbit took a while to settle down as well. So it took some doing to understand, what the final outcome was. But the orbit period change, or the change in how long it took for the object to orbit the parent body, it was faster by 32 minutes because it went closer into the parent body, Didymos, and so it traveled equal areas in equal time, and so that they shortened its path around Didymos, so it was faster. So previously it took 11.92 hours to orbit its parent body, and then after we hit it, it took 11.37 hours. And so that was a spectacular success for us. We were very, very thrilled because it was over a minute was what our goal was, and here we got 32 minutes. So it was wonderful to be participating in a project like this that was so successful. So the Italians, also the Italian Space Agency, sent up since our spacecraft crashed itself into the asteroid, they also set up a small little CubeSat called LiChaCube, and it was able to get this actual picture of the spacecraft hitting Dimorphos. So that's a cool shot of like some of the debris spewing out, and you can see the object hit sort of dead center there. So pretty good with our physics and orbital mechanics. So we were able to recently, another big thing that we got by monitoring the system in addition was that we learned that we not only changed the orbit of Dimorphos around Didymos, but we changed the orbit of the binary pair around the sun. So that was an update that just happened a month or so ago. We used stellar occultation data and radar measurements to show that the Didymos-Dimorphos binary system changed by its orbit around the sun by 0.15 seconds post-collision. It's one of those things it sounds very tiny, but it's just amazing to think we could actually have that much of an impact from a vending machine hitting a body. So it gave everybody a great level of confidence that if the Earth was ever threatened, it looks like kinetic impactors could have a real important role in at least in the small size regime. So this was something that this Dimorphos was 163 meters in diameter. So for the city killers, it looks like we might be able to, push or change the orbit with very little risk, because we don't have to use nuclear bombs. We don't have to have long lead times. We could just hit it with something like, batting it away with a hammer, essentially. And the collision had a more far-reaching impact than we had at any point initially envisioned. So this was a really crucial data point for planetary defense. And all of us who participated as team members on the DART mission were lucky enough to get our work published on the cover of Nature, a prestigious science journal, international science journal. And so we were kind of immortalized on the cover. So that was really cool. But, one of the lessons learned, though, is we have the technology. We don't have to do, that much. We can right now today save the Earth if there was a city killer or continent killer headed towards us. So we can escape the fate of the dinosaurs from the Chicxulub impact crater and not be too concerned about technology development from this point forward. We just need to do a lot more testing, excuse me. And just one final slide to sort of think about. Now, I know some of you might have been following Artemis 2 recently, where we sent humans back to the moon to orbit. It was the first time we ventured out of the near Earth zone in a really long time since the Apollo missions back in the day. And that's when I grew up. I grew up during the 1960s and 1970s, and I became an astronomer because I was so thrilled with all the Apollo work, and so it's kind of cool to be now still working, and we're going back to the moon, Artemis 2. Now it's very critical to upgrade our technologies, but also for national defense. We do need to be careful about what other countries are doing on the moon, so we have to keep pace with them and keep technological development. So we are moving forward with the Artemis program at NASA to return humans to the moon, and Artemis 3 will be launching soon, and that will again test docking maneuvers and so forth before we actually land on the moon. But it's 2026, 2027, and we're planning to have humans back on the moon. So we do have to worry about lunar impacts and making sure that things like 2024 YR4 doesn't pose a threat to potential lunar bases. So we've extended our worry zone a little bit, but then we've had a positive outcome in terms of kinetic impact or deflection. So all in all, I'd like to conclude that this has a happy ending. So thank you very much for your listening, and I'll take questions.
Thank you so much, Eileen. That was great. We did have one question in the chat. The first one that I see here is, how do you determine known percentages? How do you know what you don't know?
Yeah, that's really an excellent question, because it is one that you have to sort of put into the context of why we don't know when things are going to hit, is because we don't know what's out there yet. So how we determine the percentages is based on numerical modeling. So there are people who estimate what the mass could be out there, and they estimate the size regime. So how many are small, how many are intermediate size, and how many are large. And we estimate that to come up with the percentage that we've already discovered. But it's not definite. So that's why I'm still concerned about the 10-kilometer guys, because I think most of those we could see, but if they're in particular orbits where they're obscured by the sun, we won't be able to really tell that because we can't find those objects from Earth. And as the question is posed, we don't really know what's out there. We have to guess by numerical simulations about how the solar system formed and how much mass might have been available. So there could be something lurking that has been obscured by the sun, but fear not, NASA is launching a space-based telescope called NEO Surveyor, which will be able to look at everything and not be obscured as ground-based telescopes are by the sun. So we'll get better statistics when we have better discovery information.
Great. Another question that we had from the same person, this is C. Veen. They wanted to know, why are day and night observations shown separately?
Say that one more time. The day and night
Why
observation.
are day and night observations shown separately?
Um, I'm not sure what you mean by shown separately.
Might have been a couple of slides ago.
Let me see if I can go back. Are there any? I mean, I've only shown nighttime images that we take with telescopes. This is from the actual spacecraft, the DART spacecraft coming in. And I don't see. Veen, can you tell me exactly where, sort of give me a heads up where this slide might be that you're thinking of?
Can I talk?
Sure, sure.
Absolutely.
There was a graph earlier on that showed the entire set of bursts. That one.
Oh,
And
okay.
you've
Yes.
carefully shown nighttime versus daytime. I don't see what the distinction is in terms of what you're trying to show.
Oh, actually, it's just to make sure that we're looking both night and day, since we telescopes only have the ability to look at in the night sky, but but we can have other monitoring, all sky type cameras that have infrared sensors, and they can detect these impacts during the daytime. So optical telescopes work at night because the sun would sort of burn them out, right? But these types of airbursts or bolide events, there's monitors all around the world, mainly for actually nuclear test ban treaty work. So they look to see that no one is actually testing nuclear bombs in the atmosphere. That's what they were set up to do, and that can be day or night or whatever. But they also track day and nighttime impacts where telescopes could only do at night. These particular sensors are infrared and they can detect 24
Good.
hours a day. So we get a better
Very clear.
statistic. Yeah, so for what's happening. But yeah, it comes from the nuclear test ban treaty agreements. So yeah, that's a good question. Thanks.
Thank you. Serene Go has asked, in the scenario that an asteroid was found to be on a crash course with Earth, how would we take immediate action in the coming months/years for larger asteroids other than dimorphos? I don't have a
That's
science
good,
background, but
Brianna.
that's
Good
what I think
effort
it
there.
sounds like.
Dimorphos. Yeah, close enough, you
Marvelous.
know?
Okay, great. By the end of this, I will also be a scientist, everyone, I promise. Will we need to build a bigger spacecraft than DART? And how much resources/time will we need?
Wow, that is another excellent question, you guys. You're really paying attention today. That is something that's so very important that we actually set up an international committee at the United Nations to monitor these things. So as soon as we detect an object that is like 2024 YR4 was triggered an impact of 3%. That was early January. So the international committee called IWAN, it's just an acronym for Asteroid Warning Network. That UN committee met immediately and started working with all countries. Every single country on Earth is a participant of this network scientifically. And we all work together to see, do we need to send something to divert this object from the Earth? And how many months would it take? And we actually started planning in January while the impact was rising from 3% to 4%. What would we do? How quickly? And people were starting to share, well, we have half a spacecraft built for something else. Maybe we could use it for this. And immediately the international community started working together. It was absolutely amazing, the cooperation around the world. It just gives you a good feeling for, when we're focusing on the Earth as a community and keeping us safe from outside cosmic threats. Everybody worked together fantastically quickly. And yes, we would have to plan. I would say, normally it takes at least 2 years to get a spacecraft mission together. So this particular object wasn't going to hit until 2032. So we had some time to plan. But the sooner you deflect, the easier it is. You want to do it early where you just have to give it a little nudge and then push it away from the Earth, and then maybe have to do a second a nudge later if it doesn't do it enough. So we would want to have a lot of time. But not only does the IWAN network through the UN do these simulations, as soon as we find something, they have committees that just get deployed, but they also run every year. They have a meeting together with scientists called the Planetary Defense conference, and it's held in a different country every year. And they run mock-ups like fire drills, simulations of what would it take if something was discovered and have a particular orbit, if it was a comet or an asteroid, and how would we work together and how much time would it take? So they run drills, they run fire drills all the time. So again, you can rest assured that people are on top of it. And I think with 2024 YR4, we did have some people who were on the DART mission that were participating that said that they could get something up there and within 9 months. So that's one data point. I don't know if that would actually have happened if the impact probability kept rising instead of going to zero. But it was something that was a thrill at the time. I mean, I showed this image that we took of 2024 YR4. And I woke up on a Saturday morning and I looked at it, and this was our telescope taking this image, and it was on CNN. That the data that we were taking, and I didn't think anybody cared that much about like these intermediate stages, but I woke up, turned on the television, and I saw our picture with everybody worried about it on national television. So anyway, yeah, it's something that people are prepared and ready for quick deployment on.
Thank you for that question. Not exactly a question, but Joel gave a lovely shout out. They're very pleased to see that this is almost exactly the kind of astronomy they were studying at the Thatcher School in the 60s. So
Yeah,
that's
no, it
amazing.
really is. I mean, it's very basic. That's what's so actually elegant about it. It's not anything too difficult, right? It's looking for objects using very simple physics to get orbits, and then being very, very good at having the Jet Propulsion Lab orbital mechanics specialists predict when and where things are going to hit, and then actually sending spacecraft that hit dead on, So it's simple physics, and it can be done, at any size scale. I think it's always a thrill, like our campus observatory does asteroid monitoring every once in a while too. You don't have to be a big telescope or a fancy astronomer. We have a ton of amateur astronomers who contribute to this work. It's not just professionals for the brighter objects when they have smaller telescopes. There are a ton of amateur astronomers who contribute extremely valuable data and help us get accurate orbits on things that are 18th magnitude and brighter. And again, we go down to 25 and a half magnitude, but a small telescope, 14-inch mean, 16-inch meter, half meter telescopes can do a pretty good job. And so we have lots of people participating in this, and it's a fun project.
Great. All right, you're going to have to pronounce it for me one more time. And then after that, I will
Dimorphos or Didymos?
propose. Perfect. Okay, I got it, you guys. All right, so Rachel B is asking, the Dimorphos test was of a city killer size. You mentioned it gave confidence. We can now avoid the dinosaur scenario. Is that because the results were so much more better than expected? On an earlier slide, kinetic was associated with smaller size objects.
Yes, that's another excellent question. Let me see if I can find that slide. Did I go here? There it is. This was from the study, and yes, this would be what we could do for particular diameters up to city killer. But it was the first test, so you're absolutely right. We were just assuming that that was a size regime that this would work well, but this worked really well. So what if we launched 20 different mass objects that could hit a larger object, like a 1 kilometer? I think a kinetic impactor might be able to do something with that. But these are missions that we would have to plan for and test in the future before it becomes a critical reality. So, NASA is striving to continue these types of tests and extending the diameter range, but we had no idea it was going to be this successful. And most of that success comes from the fact that debris, asteroids are very porous, and when they're hit, a lot of debris comes off of it, which almost is like a little engine that gets created, that a difference in thrust. And so having that data point makes us a lot more confident that we can maybe, go up in size to do that. But I myself, if I'm like you, maybe, you want to really also have a test first before we're in a critical situation. So that'll be something for the future, but another excellent question.
Great. Um, Amelie Way is asking, I was wondering what the other two asteroids that were the largest size from the chart of different sizes of asteroids were, besides the one that killed the dinosaurs.
Well, we have some different craters that are fairly large, and there are other mass extinction events that are smaller than the full global scale on that. But the craters that you see in particular this graph they're fairly large over the surface of the Earth. We don't have as much data as we do for the Chicxulub crater, and that's because the Earth is constantly, it has wind erosion, it has volcanoes which resurface the Earth, and of course we have a lot of asteroids impacts that are probably under the ocean that can't be studied, and so we have a lot of indefinite information on that. We know from our studies in terms of the main asteroid belt that the largest asteroids that are there are Ceres, and which is a kilometer in size, and Vesta, which is half a kilometer in size. So we don't, in terms of the largest asteroids that hit, there are 10-kilometer in size, and one of them I believe is Themis is another large body, but you could check the JPL small bodies node, and it's got a wonderful orbit simulator where you can just kind of play and type in different things, and it will give you statistics on the asteroids. But I don't know off the top of my head in the Earth crossing zone what are the largest objects. I know the main asteroid belt, we have Ceres and then Vesta.
Great. I'll go ahead and ask our last two questions for this session. Colin is asking, in the very beginning of the presentation, you mentioned that the red spots in the sun's orbit are where asteroids are considered potentially hazardous towards Earth. I noticed some spots outside the main asteroid belt that were marked as red. How and why are they hazardous?
Such really great questions today. These are called, so the near Earth zone objects are just plain old, we just refer to them as NEOs that could hit, any of the inner planets. But the ones that are red that are outside are actually perturbed by Jupiter's resonance. And so they are in danger of potentially hitting objects in that zone, but they're red because they've been kicked out of the main asteroid belt and could hit. How many of you remember when objects hit Jupiter back a while back? Was that, gosh, is that 15 or 20 years ago? Something hit the surface of Jupiter, and we took pictures of it. A comet had hit it. So those are objects that could hit other planets, but they're not in a nice or orbital gravitational control, like a shepherd dog, keeping them safe around the sun. They kind of have more chaotic orbits because of the tremendous gravity that Jupiter has. Jupiter has a tendency to kick these out of the asteroid belt in the other direction, not inwards, but outwards. And they're usually called Apollo asteroids.
Awesome. All right, our very last questions from Celine. Are there any more kinetic orbital modifications planned, and are there nuclear tests envisioned?
People are constantly pushing for nuclear testing, especially other countries as well. Russia is still very, very concerned about Apophis, even though the predictions currently are that it will miss the Earth. They are doing, their own scientists are doing calculations, and they are planning on potential missions that would divert Apophis or test to divert Apophis. And they have not divulged whether they intend to use kinetic or nuclear. It is part of the nuclear test ban treaty to never use nuclear weapons in space. So that would have to be amended, and there would have to be different sort of regulations that would come into play. So it is possible that other countries are developing their own tests of planetary defense and are not sharing with us, but are not allowed to share with us that information. But as far as Earth, I know there's several of my colleagues who want to plan another of these types of missions, but nothing has been funded yet.
Great. If there are no other questions, feel free to come off of mute and ask your questions. But if there are no other ones, I will wrap our session up here. Everyone, thank you so much for this. It has been so amazing. Eileen, thank you so much. We really appreciate you speaking with all of us. I will let all of you know where you can find this recording. It will be on our YouTube page more than likely tomorrow. That is at SSP International. You can follow our YouTube channel. It will also be on the SSPI network. And our next Curiosity Lab will be taking place July 12th, same time, 3 to 4 p.m. And that is going to be The Secret Lives of Fungi, Genetics, and the Growing Challenge of Antifungal Resistance. And that's going to be with Rebecca Shapiro. So if you're interested in going to that Curiosity Lab, feel free to go on our website and you can register there. And Eileen, thank you so much again for speaking with us. And I hope the rest of you enjoy your Sunday.
And I would like to thank everybody for their great questions and their great attention. And thank you, Brianna, for helping make this possible.
Thank you so much. I really appreciate it. This was absolutely amazing. I learned so much, as I always do.
Go SSPers, because yeah, maybe you too can deflect an asteroid from the Earth.
Yes, I feel like after this first year of working here, I will.
All right. Thank you again, everyone. And again, I appreciate your attention and have a wonderful rest of your weekend. Bye bye.
Thank you so much. Bye, everyone.